by 9 different samples that we will provide you. Methods that you could use to identify them include density. Oh, wait a sec, I'll change my mouse cursor here. I always forget because I don't leave it. I don't like it big. I have a hard time picking things off menus with it. Density is one method. I'm going to mute here for a second because I got to blow my nose. You don't want to hear that over my microphone, I'm sure. Density is the most accurate method of identifying a material. By itself, it may not be enough. If you have 2 samples that are both steel, steel has the same density. The outlying elements are generally not in a large enough quantity to change the density enough that you could identify which one is which if you have 2 different steels. But differentiating the different materials, density is probably the best starting point. Hardness can be useful, but you need to know how that material has been treated, whether it came straight from the manufacturer, whether something else has been done to it. Relative hardness, we'll talk about that in a little bit. Color may or may not be useful. For many metals, they all look like they're the same color, so that doesn't help us. And ferromagnetism, all the metals that contain iron. You're kind of cutting in and out, so try that again.
Can you please start the recording of the lecture?
I can't because everybody can't. I got 3 sections here, and I can't. I can't record it in 3 different places at the same time, which is why I'm not, because that's not fair, because the people who entered this through section that ends in a 2 would be able to access it. Everyone else would not. So I don't want to I don't want to treat people different. It's probably the best way of putting it. That's why I'm not recording this part, okay? I checked with the IT people, and there is a way that it could be done, but it brings up all kinds of security issues, and I was told basically not to try. They didn't even explain how to do it, but there's a way to do it. It would involve essentially other people getting into another section. I asked all about it quite some time ago, actually. I had an extended discussion with IT about it, back and forth. And there's no secure way to do that. So sorry about that. I will actually, at the end of it, I will actually post it. The notes get posted, and the exams are based on the notes. All the metals that contain iron are ferromagnetic. Iron attracts a magnet. The other 2, most of the non-ferrous metals don't attract magnets. The 2 exceptions are cobalt and nickel. If you remember, we covered that in the notes last week, actually. And I could be wrong about that, but I'm pretty sure that it's nickel and cobalt that are magnetic, even though there is no, technically there may or may not be iron in them. Nickel is alloyed with iron, but it doesn't have to have iron in it to be magnetic. And cobalt may be an alloying element with some steels. I'm not even sure about that. I'm not an expert on what we almost anything that can be alloyed with iron has been alloyed for properties. But you'll know for sure if it's magnetic that it probably has iron in it, but it could be something else too. The place to go you're going to need some reference information, and the place to go is something called ASTM tables. ASTM is an acronym that stands for the American Society for Testing Materials. You cannot access their information for free. You have to pay. The good news is that Sheridan actually subscribes specifically for this course and other courses to ASTM databases. So when you need reference material, you need to get to Sheridan's reference material online, and we have a lot of stuff online, trust me, because I've used some of it, that we've actually paid access for to get. Okay, so when you're looking for reference data, that's actually the best place to look, because it's genuine data. It's the best reference data you can get. The note at the bottom is kind of important. When you come to the class to do Lab 1 next week, week 3, it is very much to your benefit to have a copy, electronic or a paper copy. Doesn't matter which. You only need one for an entire group, because you're going to do the lab as a group. We'll talk about more about the lab experiments during the lab class, which is tomorrow. But it's of great benefit to have Table 1, which I have actually personally created for you in order to collect all your data in one place. It makes it much easier to record all the data while you're doing the experiment. So it is beneficial to have either a hard copy or a soft copy. If you're going to use a soft copy, it's much better to be using it on the big screen of a laptop rather than your handheld device, because it's going to be a little hard to work on that little 5-inch screen or whatever it is. But having access to that table will really make things much easier for you. Color. Cold finish steel will have what we call a metallic luster, silver, various levels of relative shininess. You notice the parts on the bottom left here are almost like what we call a mirror finish. You could almost see your face in them. This not so much, and that one's a dull finish. So for these three, and I would take an educated guess that these are actually different steels, different grades of the same steel, probably different steels altogether, or they've been processed differently. But for these, using color to identify them is useless because they all look roughly the same. Hot finish steel, which is not shown here, has what's called a black mill scale. You have to machine it off. It makes a mess. Hot rolled steel is the least expensive steel you can buy. And it's not really used much for things we manufacture because it's the least, when you buy the cheapest you can get, you're giving up something, which is properties of strength, the properties that we need when we build a piece of machinery. It's false economy to buy the least expensive materials you can possibly get to make something like that, unless you don't want it to last very long. You need to make some little thing that if it lasts a couple of hours, that's okay. If it lasts a day, that's okay. Most of the things that we make are intended to last for years and make thousands, hundreds of thousands of parts, not 5, and then we throw it in the garbage. if we're doing prototypes or something like that, and we know we're going to just throw it away once we've proven the concept, then that might be okay to use. Even then, you probably still wouldn't use hot rolled steel. It's the cheapest of the cheap, and really, I've never seen it in any place I've worked to be used for making parts. We buy higher quality steels. But if somebody is, all they're concerned about is how much the raw materials cost, then yes, they might be using it. High chromium, high nickel content, or stainless steels will all have a shiny silver appearance. These are all related to one another. They're not exactly the same thing, but high chromium steels, you need chromium to make stainless steel, but there are also high chromium content steels that are not stainless. They behave like a stainless steel. High nickel content steels are not technically stainless, but they behave like a stainless steel, and they'll all look similar. Of these items here in the bottom right corner, this piece of tubing is laying on its side. I can tell you from the appearance of it that it's probably a high nickel steel, because nickel gives a kind of a dull silver finish as opposed to the stainless materials, which are more shiny or shinier. In many cases, color won't help us to identify a metal. It just isn't going to be of any use. Remember that density is a physical property for all three states of matter, whether it's gas, liquid, or solid. We define it, and if you get a definition question to define density, all you need to say is that it's the mass of a given volume, or just D equals M over V. It needs to be a unit of volume. You need to, if you're calculating density, you need to make sure that the units are correct to give you density in the units you're looking for. Are you going to find a reference density in kilograms per cubic meter? Probably not. More likely it'll be in grams per cubic millimeter or cubic centimeter, but not per meter. That's a bit too big of a volume. So be very, very careful to make sure that the units you get when you're calculating densities give you the equivalent to what's in your reference that you have found. Because you need to refer it back to something that's published that says this is the density of steel, or this is the density of this particular steel, or aluminum, or whatever it is you're trying to find. All ferrous metals are attracted to a magnet. Most non-ferrous metals are non-magnetic, and there are two exceptions. And check the reference, but I believe it's cobalt and nickel. And it's from the notes from last week. It's actually in there about the two exceptions, just to make things a little more difficult. Chemical reactivity, I've never actually seen this done. So if you take a clean surface, you have to polish it first, and put 6% nitric acid on carbon steel, it'll discolor, and it won't discolor stainless. Well, that doesn't really help us much. Nitric acid is an acid you do not really want to play with. It is one of the more reactive acids, and 6% is a fairly strong solution. Nitric acid is really dangerous. It's not one to play with, okay? You really shouldn't play with acid anyway, but it's probably absolutely one of the ones you don't really want to have around, unless you're working in a chemistry lab under controlled conditions and storing things like acids in. There are special cabinets that we put things like nitric acid, sulfuric acid into, that keep everything safe just in case something goes wrong, like we have a leak or a fire or something like that. They're the cabinets that we store those things in are actually quite expensive because I've purchased a couple of them in my time when I worked in the industry. There's a reason why they're so expensive, because they're meant to keep everyone safe just in case something happens, and to keep the firefighters safe if they have to come in and fight a fire. And we've got fire around hazardous chemicals, because we have to keep them safe too. Hardness on the go. Relative hardness. This is one of those things that you can do. It's not really a it's something you can do with just tools that are handy, but it's not a formal experimental type of thing to do. And what it amounts to is, if you have 2 or more samples and you know that one of the samples is harder than the rest, you take something like a file and you run the file across a surface of the material and see, without putting excess pressure on the file, because if you push down, of course, there's a chance to cut deeper. But basically, you run something that's abrasive like a file over a part of the sample and see how much you can impact the surface and take some material off. And if you do that, of course, the one that's relatively hard will produce a smaller indentation or cut and produce a smaller amount of filings. So it's a quick way to find out, I have 5 samples and this is the one that's harder than the rest. So we call it relative hardness. You're comparing, maybe to find the one that's been heat treated and hardened, and somebody's mixed them up somehow. Although there are probably other ways to find that out. But anyway, this is like a, quick less than a minute to just find out which one's the hard one. I misplaced them. I dropped them on the floor and I don't know which one is which. For experimental use, not really used. Okay, it's more for, as I said, we've mixed the parts up, which one's which. And we know that there's a difference in hardness. What is hardness? The resistance of a material to indentation or penetration. And these are both really the same thing. Indentation is to put a dimple or a dent in a part. Penetration is if the part's thin enough and soft enough, it goes right through completely. So you penetrate it, you put a hole in it. By different means, like some kind of an abrasive, whether it's with a file, a piece of sandpaper, drilling. And if it's hard, you won't be able to drill it unless you use a special hard drill bit, like carbide, or I don't know if they have ceramic drills. I don't think they do. Carbide probably. Impact, hitting it with something else, it's hard, and putting a dent in it, scratching it, or just wear, as in parts that we install in a machine. If it's got a higher hardness, it means it will wear longer, because it'll take longer for it to wear rubbing against something else. So in short, hardness refers to material's ability to resist being damaged, dented, worn away, or deteriorated as a result of an applied load. And probably some kind of an abrasive or a rubbing function. We measure hardness by different tests, and there are more. These are the more common ones. Brinell. We have a Brinell tester in our lab, but we don't use it. It works, but we don't use it. We actually have a Knoop tester, which is used for what's called micro hardness, which is an experiment where we surface harden parts. It's actually experiment 7, if I remember correctly. And Knoop is actually done under a microscope. And it's because it's doing a very, very tiny part of a component. And the area that you're measuring is so small, you actually need a microscope to observe it and to measure what happens. Rockwell is the one that you will hear about the most, and it's the one that's used the most. And Vickers was actually invented in Britain, named after somebody named Vickers, I'm pretty sure. And it was the original way that we tested hardness quite some time ago. However, it's been superseded and taken over, and Rockwell's in much greater use than Vickers now. There is no standard hardness scale that exists that relates these to one another. You will find, if you look on the internet, you'll find tables that attempt to relate these different scales to one another, but they're really just an estimate. When we're doing hardness testing, the best way to approach hardness testing is to choose whichever piece of equipment you've got and stay with that piece of equipment. So don't take, I don't know, a Vickers tester and try to convert Vickers readings back to Rockwell. Whatever machine you've got is the one you use, and probably Rockwell, because it's just the one that's most common. Rockwell was actually named after not a person. There may have been a Rockwell person, I don't know that for sure, but it's named after a company called Rockwell, which I'm not even sure if they exist anymore. I think they've been bought out and their name may have been changed. But it's actually named after the company that invented it or created it. But you can't relate between these. You can kind of estimate, but it's not really valid. So, and Canupa is strictly for micro hardness. It's for a very tiny surface area. Rockwell's the one that's in greatest use. This is we have two of these in actually Rockwell testers in the lab. We have a more modern version called, it's made by Mitutoyo. These are sturdy. I wouldn't say they're not, I wouldn't say that you can't break them, but it takes some effort to damage them, although it is possible to damage them. But they are simple enough to use and sturdy enough that lots of companies that don't have anything to do with hardening or heat treating materials have one, because they're, in relative terms, relatively inexpensive to purchase. You purchase them used, you can have them refurbished, calibrate them, and just use them to do hardness testing to see if materials you've got are a certain hardness that you are looking for. The Mitutoyo version that we have of a hardness tester works in Rockwell. It's actually a laboratory instrument. It's automated, it's electronic. We use it for Lab 1, I'm pretty sure. I'm not sure where it is right now. It might be in the wrong room to use it. But we do actually use the Mitutoyo, just because it's really a laboratory instrument. These are still suitable to use. Nothing wrong with the results they give. But we'll get into using them more. But this is a much sturdier item. And we get into the lab, which will at least make sure you understand how to use this, because you may see this in the workplace. The Mitutoyo, unless you work in a laboratory, you would never see one. You wouldn't have it. They wouldn't put it out on the floor. These things, you could put them out anywhere, because they're not as dust sensitive as the laboratory instrument. Doesn't need to be kept in an air conditioned environment like electronics need to be. This is what's called a Shore-D tester. You're seeing a kind of a picture of a little bit of it. This is never used for metal. Metal will damage it. And inside this brass tube here, there's a very fine point, which is pressed, and this thing has to be calibrated. Our lab technician will make sure it's calibrated before we try to use it. It's used only for polymers, which includes all the plastics and rubber. We never ever use metal on this. And we never use plastics or rubber on this either, because this thing will damage the materials. And this one, metal, will damage the actual testing unit. So strictly for plastic and rubber. And you will have 2 plastic samples to identify. So we'll hardness test them here on this machine. We'll go into that. Actually, it's in the lab document. So what's the relationship between hardness, ductility, and strength? As we increase hardness and strength, ductility will decrease. And ductility is the ability to shape a material and have it be deformed into a more useful shape for us and retain that shape. Materials that aren't ductile, we can't form them. We can't change their shapes. So low ductility, the opposite of ductile is brittle. And brittle's not really a desirable property, because if you have brittle material, as you put a load on it, when it fails, it will fail. It'll fail spontaneously. It'll be holding on, and then suddenly bang, and it's just broken. So that's a catastrophic failure. We would prefer, if possible, to have enough ductility that if a part is going to fail, it will somehow give us some visual clues by deforming in some way, so that if we're paying attention, we'll get to see it deform slightly in some way, so we can do something about it before it actually fractures on us. But if we desire a great deal of strength so that the part survives heavy loads, and we need it hard so that we can get wear resistance, we're going to have low ductility, it'll be brittle, and when that part fractures, it's going to be a catastrophic failure. It'll be working fine, it looks nice, and then bang, which may cause us some kind of other serious problem. We don't really want, but choosing materials and design, you'll choose the properties that you want during the design phase. There will always be some things that are not desired, and you have to balance off what you need, what you have to have, and be accepting of properties that you don't really want to get. You want really high strength and high hardness, you're going to have brittle parts, and you may have to have whoever is using that equipment that has that very hard and strong part pay more attention, or replace the part before you expect it will fail. And in many cases, and you'll discover this in Mechanics and Materials, which is a Term 4 course, we can actually predict fairly accurately with equations that have been refined over many, many years. We can predict failure of parts. Not exactly to the second or to the minute, but we can, usually based on cycles actually, we can predict fairly accurately how long a part will actually last, as long as we know the loads it's subjected to, and we know the properties of the material. You'd be surprised what we can determine and know is going to happen. Lab 2 involves welding, and you're going to study. This lab is virtual, and it's virtual because there is constant handling of samples, and if anyone in the group had been exposed to COVID, this would be a super spreader. Everyone else that you're working with would have it, because you're close together, you're constantly handling things. polishing, etching, putting it at the microscope, hardness testing. It's just, we saw this one as one that with COVID-19, we couldn't have people working on it together because it would just be, it would be a recipe for disaster. And of course, if we were to spread COVID among our student population, the province would probably tell us we can't have students in the building anymore. So we're keeping you safe, which keeps us able to have students in Sheridan. Because a year ago, March, when they shut down, the first thing we did was they actually shut us down. The province, it was a Friday morning, and I had a group doing a lab. And one of my students said, we're shut down. And we were halfway through. We 2-hour class, we've done an hour. And I said, we're here, we're going to finish. And then, of course, a couple of minutes later, the announcement came out that at 4 o'clock, Sheridan was closed to anybody being inside the building. Unfortunately, we'd already gotten 3/4 of the way through the labs by the time they kicked us out. And we improvised very quickly. These are pictures under a microscope of different structures of steel. Ferrite is iron that has no carbon content in it. So this is a sample that has been polished and then etched, and we'll get into how that's done later. But in order to look at the microstructure, we actually polish and then etch to allow us to actually see it under a microscope. And this is iron crystals with, these are called grain boundaries, and it's pure white with the grain boundary is dark between. The etching actually makes those grain boundaries show up. So there's no carbon at all in this. As we add carbon, now this is a different piece of steel. You can't turn this into something else. So this is done by the manufacturer. As we add carbon to steel, when it's produced, the carbon starts to put in these little lines. And if you notice, this still has this 100% perlite, which means it's saturated with carbon within the crystal structure. As the manufacturer starts adding carbon to a steel, as he produces it, it'll start putting in these little straight lines inside of the crystals. When they produce a steel that is at 0.8, so 0.8%, if you think about it, that's not very much carbon. We're talking 0.8%, really almost nothing. We saturate the crystals with these, we call them lamellar because they run parallel to one another. We start to fill in the crystal. At 0.8%, this is saturated. You can't get any more carbon inside of the crystal structure. As more carbon is added, since these little crystals are all saturated, it starts to fill in what's called the grain boundaries between the crystals, and they start to actually, and when it goes into the grain boundary, it's called cementite, also known as iron carbide. These are both the same item, just expressed a different way. But it starts to fill in the grain boundaries with carbon because these guys are saturated in the crystal. And as you fill in the grain boundary, it starts to compress the crystals themselves, causes some compressive tension or stress in the material, and it makes it harder. So it makes the metal harder. And there's something called martensite that we'll cover, which is actually hardened steel. But these are the phases of steel. Now, this picture is not the greatest. The dark areas, this is 0.2%, so 0.2% carbon. So it's not saturated yet. These, if this was polished better and it was a better picture, the dark areas would have those parallel lines, but it's not polished well enough and not magnified enough to show them as a series of straight lines starting to fill in the crystal. Remember, you need 0.8% to have these completely filled in with those lines of carbon. This is another steel which has been produced at 0.6, so we're about 75% saturated, and the white areas that are left are parts of the crystal that don't have any of these lamellar fillings in, and you can't see the straight lines here because there is actually, it looks just literally like this with alternating white, which is ferrite, and then the carbon filling in between the lamellar bits. You know, we're getting, this is not a great picture either, actually. I should probably source a better one, replace this. It gives you an idea anyways. If this was 0.8%, if it was produced as 0.8, the whites would all be missing because it would all be full of carbon. And then it would all be filled in with the darker colors, which is perlite. So there's still some free ferrite, as we call it. It hasn't been linked up with carbon to make perlite. So pure ferrite, pure iron, there's no carbon in it. This is, and if you notice, these guys run in different lines. Where the lines change direction, that's another crystal. So with the lines all running this way, this is one crystal, and if you notice, they're different sizes. This one's running at, I don't know, about a 60-degree angle to it. Every time the angles, every time the lines change direction, it's a different crystal. So these are all different crystals zoomed up. This is a picture of martensite, and the way we can tell it's martensite, and this is not the greatest picture again, there will be little, we call them needles. These little long things here, they look like a pine needle. That's actually what you're looking for. And I should probably get my own pictures. I didn't put these notes together. I've got much better pictures somewhere else. I have to find them. This is what's called the iron carbon diagram, and we'll take a look at it not for at least a few weeks, and I'll point out some things about it, but I'm not going to put much emphasis on the iron carbon diagram because it's not something you need to know a little bit about it. You need to know that it exists, but you don't need to go memorizing things about the iron carbon diagram. So carbon steels at room temperature are generally a combination of ferrite, perlite, and what's called cementite, which is the stuff on the grain boundaries that's being filled in with carbon. Now, if you remember, and these are microscope pictures of steels with a different carbon content shown down along the bottom legend here. So at approximately 0, not absolute, but very, very close to 0, all we've got is just ferrite. And we polish and etch the material. There's no carbon in it. As we increase the carbon, which means it's another product, we can't turn this into that. Okay, these are all made by the manufacturer. We're just taking and polishing the steel and then etching it and getting a picture of what was existing. We can't create one from the other. It doesn't work that way. The steel manufacturer did this. So at approximately, this is approximately 0.5% or 0.5% of carbon. We've got some perlite starting to fill in to the crystals, which are still have a great deal of ferrite in them. When we get to 0.8%, and this is meant to be on that dotted line, and you'll see when we talk about it, the iron carbon diagram, this dotted line is actually saturated perlite at 0.8%. And here we've got the crystals that are full of perlite. We can't get any more perlite in the crystals anymore. We can't get any more carbon inside the crystals. As we increase the amount of carbon, or as the manufacturer gives us more carbon, and here we're at 1.5%, the additional carbon can't go into the crystals. It starts to fill the grain boundaries, and they start to get heavy. When we etch it, it actually shows up as here. You can tell that they're divided primarily because the perlite in the grains actually go at different angles. They don't end up going in the exact same direction on adjacent crystals. Why? We won't talk about it. It has to do with how the grains grow as the steel is cooled from the temperature it's manufactured at, which is over 700 degrees Celsius, over 1300 Fahrenheit, but 7 something, I forget. Anyway, don't worry too much about the numbers. So as the steelmaker has more carbon, the individual crystals are saturated with carbon, and it starts to fill in the grain boundaries and compress these crystals. When we get to just a little bit over 2%, that's the end of steel. Steel can't have more than 2.1, 2.08, depending on your reference. And don't worry about memorizing this. We're not going to ask you to know it for an exam. But once we pass here, this is cast iron. And here we've got cast iron at what, about 3.2%, because this is 3.5, which has much, much more iron carbide or cementite in the grain boundaries. Hard, brittle, not desirable, and generally we're more likely to choose steel rather than cast iron, because cast iron is brittle. Cementite is the hardest structure, which is the stuff that's in the grain boundaries, also known as iron carbide. At 6.67% carbon, you're completely saturated. That's it. So iron will not accept more than 6.67, which is why the iron carbon diagram goes to 6.67 and then it stops, because you can't get any more carbon in it. It's impossible. We'll talk more about the diagram in detail around week 5 or 6, I think. I forget. Maybe a bit, maybe after the midterm. But I'm not going to put this on the exam and make you regurgitate this stuff. What is welding? Welding is the process of joining 2 or more pieces of material by the application of heat from either burning 2 gases to generate heat, creating an electric arc, induction, which means we're going to create a magnetic field and create an inducted heat, or soldering, which is a low temperature, either electric or burning a relatively low energy gas, usually propane or something similar to propane. But those are the methods to apply heat. We will stop here. and continue tomorrow during the lab class. And we'll finish up this and talk in great detail about the labs next week so you know exactly what to expect. Okay? So have a good one day, actually, because it's we'll be talking again tomorrow. Stay safe. Okay? Things are getting much, much better. I don't know whether you would know. I don't know how it's been conveyed. I actually got an email about it, but Sheridan is setting up a vaccination clinic in the gymnasium at Davis, and international students are welcome to go. And if you haven't had a shot, it would be a good idea for you to try to find a way to, no, nothing on campus this week. No. Labs don't start until week 3. Okay? And we'll talk in detail tomorrow, and it'll be recorded. Okay? I'm recording those lectures because they're individual by section, so everybody gets treated the same. Everybody gets a chance to open them after the fact. It's unfortunate I can't have you all in one recorded session, but as I said, there's all kinds of privacy issues, and I got a pretty stern lecture from somebody about not even attempting to do. I figured out how I could do it, and then I was told, do not do this, because I could seriously, basically, corrupt Slate if I did it. So I like working at Sheridan. I've been here more than 10 years, and I plan to keep going until I retire. So I don't want to get kicked out for doing something silly. Anyway, check into the ability to get vaccinated, because if you haven't had your first shot, it's a good idea to get one. At least it gives you some protection. Getting shots doesn't mean you won't get COVID. What it does is the purpose of it is to make the symptoms you get not as severe, which means you don't hopefully end up in the hospital in intensive care, which, based on what I've heard and read, things will never be the same if you end up in ICU. So you really don't want to get to that point. And you guys are young, you got your whole life ahead of you. So you don't want to start with something that's debilitating when you're, still in your early 20s or maybe even younger than that. So take care, and we'll talk tomorrow. Okay? Bye for now.